Okay, off we go. So, last time we were talking about different ways to draw pictures to help us understand functions. And again, the reason we have to be really careful about that is because there's this implicit subtext in single variable calculus courses that picture equals function. Because after all, there's only one kind of picture they ever draw, pretty much, and so you can kind of get away with this just untrue position that, if you have a function, there's a particular picture that you draw, and that's it, end of story, right? And so you get too accustomed to that, and implicitly then you'll always assume subconsciously that when you look at a picture that you're looking at a graph of the function in question. And it's really wildly, tragically not true. So, if you are looking at a picture and you want to know, what function to talk about, keep in mind there are several candidates, and you have to choose appropriately depending on what you want to do. So this is one of my favorite examples. This is an example I like so much. I have made quite a few exam questions out of basically this example in some sense. Different curves, different, lines or whatever, sometimes surfaces. But the basic idea of this example is here's a geometric object, in this case a line, and the loosely stated question is, what function should I study the calculus of to understand this line? And, the answer is, there's a bunch of different functions that you can relate to this line. It's just that they relate in different ways. So, in particular, I claim that that line, this one line, just to be clear, that line with that equation, on the one hand, it's the graph of that function. On the other hand, it's a level set of that function. On the other hand, it's parameterized by that function. There's three completely different functions. Not only are they different formulas, which you notice right away, they don't even have the same domain and target. Right? These are really, really different functions. And yet they all describe that same line in their different ways. Right? So what you have to worry about, again, when you're trying to understand this geometric object, and very often we try to understand geometric objects by using the fact that certain geometric features of the object in question will relate to the calculus of the function, right? But again, which function? And so roughly speaking, as we go through this course, we're going to develop a calculus of graphs, things that you can do to the function whose graph is your curve, right? That will tell you certain geometric features. And there will be a completely different, importantly, completely different calculus of level sets. And there will be a completely different calculus of parameterizations. And if you apply the wrong kind of calculus to the wrong function, then you're going to get a bunch of nonsense garbage. It's a very, very dangerous problem. Again, I've been teaching multivariable calculus for, decades now, and I've seen this happen a million times, and I hit this topic more and more. You can what happened here? That was weird. Okay, I guess, that's weird. Let me make sure the recording is still going. Yeah, okay, we're still going. That was just a projector thing. So I've seen this happen a million times, and over the years and years, the amount of time that I spend on these distinctions and these, exactly particulars has been sort of steadily rising, and the number of tragedies that I see happening on student exams has been steadily decreasing, but it's still not zero. And so be warned, heads up, you got to be really careful about this. Something to keep in mind. Now, how do I find these functions? I'll say a quick word. Some of these are easy. How do you find this function that parameterizes the line? Well, that was the topic of a few days ago, and we've already talked about that, and y'all can think through those details for yourselves. And by the way, this is only one of many parameterizations. You might get a different one than I got here. Totally fine. how do you find this function whose level set is that thing? This is actually pretty straightforward. You can almost probably see it happening. Just keep in mind that level set means that you're going to set it equal to a constant. And so you then just have to write that down and now reverse engineer what constant can I put here to make this equation the same as that equation. Well, clearly 6, and there's no problem, right? But now you can turn that around and say, what can I do to this initially given equation to put it into a form where it's some function equals a constant? And, well, good news, it was already in the form where some function equals a constant, right? And so that naturally gives rise to this function. Okay. Likewise, analogously, but differently, when I look at the graph of this function, I get the graph by saying I'm going to set this value of this function equal to a new variable. Wait a second, this is a function of only a single variable, x, and right, this is a function from R1 to R1, so I guess I'm free to call this new variable, free to call it y, and you can do a pretty easy little bit of algebra and note that that is equivalent to this. So easy to confirm by just literally writing down the graph of this function that it's equivalent to this equation. How do you go the other way? How do you find this function in the first place? Notice that all you have to do is just solve for one of the variables. In this case, I solve for y, and in solving for y, I get this. Okay, so make sure to use the right function for the right purpose. And again, we haven't yet developed any calculus of any kinds of constructions, right? But as we go through and develop calculus of graphs, calculus of level sets, etc., make sure to file those appropriately in your mind and use them appropriately. Okay. All right, real quick little algebraic trick to observe. This is very handy in some circumstances. This is not hard algebra. And again, like the warning I gave you all previously, that what's hard about this stuff is interpreting things strictly, carefully, making sure to get it right. The devil is in the details, right? So anyway, I'm going to start this with an innocent observation that these two equations right here are equivalent. I think that's a pretty easy pitch. Right? I just moved sort of one term to the other side. Hardly anything happened. Both of these equations, I mean, they're the same equation, kind of. But let's say this equation, these equations, whichever you prefer, they'll describe some geometric object in Rn plus 1 because there are n plus 1 different variables here. And I'm just going to call that S just to give it a name. So this surface, let's call it hypersurface, whatever. What can I say about it? Well, on the one hand, look at this. I've got one variable expressed as a function of the others. That means that it is a graph. And specifically, this is the function whose graph we're looking at. This thing S is literally the graph of F. However, let's look at this exact same equation. Let me written a little differently, but I mean, come on, basically the same equation. As it's written down here, you see it's written as a level set because I've got expression equals constant. So this same surface is also a level set of that function. And I have to emphasize, let's be really emphatic about this, this is not the same function. Right? I mean, look at the formula for it. This thing called G, I mean, it's got a lot of F in it, right? But there's a Y in here in the formula for this function. There's no Y in the formula for this initial function, F. F is a function of only n variables, x1 through xn. This weirdo is a function of those and one more. Y is an input variable for this expression, for this function. Right? So, neat fact, what this means is that if you are looking at a graph, any graph, just kind of move terms around a little bit, reinterpret your equation as being a level set. Notice that it's now a level set of a different function, and this allows you to reinterpret something presented as a graph as instead being a level set. And why we like this is because sometimes, even if what comes to you, it comes to you as a graph, sometimes you might want to be able to use the calculus of level sets. Calculus of level sets is pretty awesome. There's some pretty cool tricks about level sets. So this is a way to convert the question into a different form, and then you'll have a completely different set of tools available to you. So for example, here's a function. Here's the graph of that function. Maybe we want to know some stuff about this graph. Okay, fine. Well, here you go. Nothing happens here. This is just moving things around. That's barely worth mentioning, but nevertheless, there you go. Equivalent equation. And check it out. It is, in fact, a level set. See right there. Stuff equals constant. It is a level set, and specifically, it is a level set of that function. So while, if you want to understand this surface, whatever that surface is, we'll come to that in a few minutes actually, you can apply the calculus of graphs to this function, or you can apply the calculus of level sets to this different function. And you'll be able to draw different geometric conclusions that the calculus of graphs from up here might just not have told you at all. Okay, really cool trick, yeah.
Will the question, like whatever problem you have there, does this to which function to use?
Nope. But well, maybe not. Who knows? No promises. But very often, I might just give you an equation and say, hey, tell me about this surface, and you've got to figure out. Would it help to view it as a graph and apply the calculus of graphs? That would be part of the question. Yeah. Right, yeah, sure, no worries. Okay, now, one of the bits of good news about this, I've already noted, is that this works for any graph. And I think you can see it's not that hard to see that this works for any graph, because any graph, you can pull this little algebraic quick one, right? All you got to do is move one term to the other side. You can literally always, if you're looking at a graph, you can do that. And you can rewrite it as a level set. Can you go the other way? Not necessarily, because not every function whose level set you're looking at is as algebraically nice. So here is a tragic example. Here is a function of which we are looking at a level set. Right? There's a level set. And you can see that this level set is this circle. Can I view that as being a graph? Well, it's a non-starter. It fails the vertical line test. No matter which direction you go, crash and burn, game over, we lose. It's not a graph of anything. So not every level set is a graph, even though every graph is a level set. So maybe you got to keep that in mind. Okay. Next kind of general topic, we're going to talk about how to deal with equations of several variables, in particular equations of three variables. Now, you all have a lot of experience from high school way back when of if you see an equation of two variables, not just any equation of two variables, to be fair, right? But there's a lot of equations of two variables that you know how to look at it and say, okay, this is a circle or an ellipse or a parabola or, a line, various different curves that y'all are familiar with. If there's three variables, the equation of three variables is going to describe a surface. And what y'all have not probably seen much of, if any, is how to identify the surface described by an equation of three variables. So this is going to have certain features in common with all that high school stuff. Namely, there's going to be various tools for your toolbox. It's not going to be a complete like the following will allow you to draw a picture of any possible surface. No, it's just not. These methods are not that perfect, right? But nevertheless, I'm going to show you some tools that will allow you to answer these kinds of questions in a lot of cases. The book has nice examples in there, and I encourage you to look at that as well. And again, keep in mind, I pick and choose. I only get to spend so much time in class, and I have to choose the topics that I think are the most constructive. So don't forget about what's in the book as well. Okay, this first observation is about rotations. And here's the big point. Sometimes, surprisingly often actually, not always, but surprisingly often, your equation will involve x's and y's only as part of this special form, square root of x squared plus y squared. Sometimes, surprisingly often, again, that'll be the only way that x and y appear in your equation. And when that happens, it's awesome. It's a super cool conclusion that you get to basically snap your fingers and draw a conclusion that surface is rotationally symmetric around the z-axis. Really cool conclusion. Now let's talk about why this is true. Let's see, there we go. So let's entertain, let's see here. Let's do it like this. Let's entertain this point. Here's a point. And I'm going to take that point and I'm going to rotate around the z-axis, producing a whole bunch of other points, but in particular, just to have one to talk about, there's that other point. Okay. Now, these 2 points, different points. They have different x coordinates. They have different y coordinates. They do have the same z coordinate, that's nice, but they have different x and different y. And the first temptation is to say, look, these are different points. I'm going to be plugging in different numbers into the equation. The relationship, the arithmetic of the one, the arithmetic of the other, what are you going to do? Right? But even though these have different x and different y, notice, because one is a rotation of the other, that means that these two distances to the z-axis are the same. That means, of course, now that distance is this square root. That means that expression is the same. That is the only way that x and y appear in the equation. And, of course, you'll also notice, because these are rotations, they also have the same z. And so even though the x and the y are different, as far as the equation is concerned, you're going to get the exact same, and the only way that the x's and y's appear, you're going to get to the same value of this and the same value of that, and the whole expression is only made up out of these two numbers. And so these 2 points, different though they are, they're either both going to work or they're both going to fail, because in both you're doing pretty much the same arithmetic. So it's a really neat observation. Very cool that that this one easily checked condition. Let me come back up to it here. X and y appear only as part of that form. You can eyeball glance. And you get this huge payoff of this powerful geometric feature of rotational symmetry. Now, here, there's a different way that you can come at this if you like. Suit yourself. This is just a different way of thinking about it. If x and y appear only as part of that form, just think about how you would convert that equation to cylindrical coordinates. Well, every time you see square root of x squared plus y squared, you just kind of write down r. You'll never write down theta. There are no other x to be r cosine theta or y to be r sine theta. So thetas will just never show up in the equation. So an equation, as we describe up here, has no thetas in it, and again, therefore, rotationally symmetric. So take your pick, whichever one of those arguments you like better. They're both nice. Let's see an example of this in... I got a little bit ahead of myself. Here's why we care about rotational symmetry. If you have a surface that's rotationally symmetric, this is purely geometric appeal. You just have to visualize in your head. If a surface is rotationally symmetric, then it is a rotation of a curve. Just got to think that through. Specifically, it's a rotation of any one of its cross sections by any plane containing the axis. It's just geometric appeal. All right, now we're ready to actually put this into effect. Here's that equation. I've made reference to this equation a few times now already, and last time, I guess it was, I made an argument about horizontal cross sections of graphs being level sets. Y'all remember that one? Just a few pages back, right? And I used this as an example, and I apologize. Okay, well, eventually we'll see how this is actually a kind of a bowl like this. And now we're armed enough to be able to argue this. So here we go. Step 1. This is rotationally symmetric. Look at the x's and y's. There's no x's and y's anywhere in that equation other than part of the special form. And just keep in mind, by the way, I could rewrite it if you don't like it as I've written it. I can rewrite this as z equals square root of x squared plus y squared quantity squared. So there you go. There's your the special form. And by the way, anytime you can rewrite an equation truly equivalently, right? No funny business. No sweeping minus signs under the rug or something like that. But if it's truly equivalent, as this is, you can apply the rule to the equivalent form just as well as the original form. Totally fine. Okay, so whatever this is, it's rotation. Did I hear a question? I'm sorry. No, okay. Sorry, my ear's playing tricks on me. If we see that form, we know that we've got something that's rotationally symmetric around the z-axis. All right. Next, I get to decide any plane containing that axis. To be fair, so you can't pick the xy plane. It's got to contain the axis. It's, again, geometric appeal. But so I'm going to pick the the yz plane here. No particular reason. You got options if you really want to pick. The XZ plane, cool. I'm going to do that in one of my later examples. Suit yourself, it doesn't matter. I do recommend always picking a coordinate plane. I mean, if you just want to be a masochist about it, you could pick that angled plane, I guess, but that's just going to make your life difficult for no apparent reason. So let's not. Right? Anyway, for this example, we're going to pick the YZ plane. And here's how easy it is to find the cross section in that YZ plane. There's the YZ plane. Plug it in to your original equation. And notice you get z equals y squared. That's a familiar form, right? That flashback to high school algebra. That's a parabola. Like so. Okay, so reminder, what are we doing? We know that this thing is rotationally symmetric. Therefore, we know it's a rotation of its cross-section. We've now identified that cross-section. And now all I have to do is rotate that orange cross-section, and again, geometric appeal. What happens when you take a parabola and you rotate it around the z-axis? Well, yeah, you're going to get a bowl-like thing like that. So our original equation is this rotated parabola, and by the way, this is called a paraboloid. So there you go. That's how we knew previously when we used that equation that it would be this surface. Everybody happy with that? Okay. It's a real slick argument. Underappreciated. Undersold, I think. That's why I like to push this harder than the book does. I think there is an appearance of this in the book, but they don't flesh it out as much. Okay, another example. Now, I'm not going to. I'm going to go a little quicker through the details on this one. But again, x and y appear only in the special form. Emphasis on the word only. It's not good enough that x and y appear in the special form. It has to also be that there are no other appearances of x and y. You can't have an e to the x over here, or cosine of x plus y. Nothing, no other x's and y's other than part of the special form. We're good here. So we're rotationally symmetric around the z-axis. Pick your favorite plane. Just to show I can, here I will do the the xz plane. Not that it matters. Take that, plug it in, see what it turns into. Here we get a hyperbola. Flashbacks to high school algebra. What they used to call Algebra 2. Lord only knows what they call it now. Right? And that is a hyperbola. And now we have, again, this sort of geometric challenge. You've just got to think to yourself, what do you get when you take this hyperbola and then you rotate around the z-axis? That's how our game works here. When this rotates around the z-axis, and I claim that you get this, well, that wasn't my best part. Something kind of like that. And that's what this is, and it's, by the way, called a hyperboloid. No surprise that it's called a hyperboloid. After all, it's clearly a rotation of a hyperbola, right? So natural terminology. The one sheet business is to distinguish it from a different kind of hyperboloid that we're going to see in a couple seconds. Everybody happy with this one? Yes?
Where in that hyperbola is the 1?
Where's the what now?
Where in the hyperbola is the 1?
You're talking about this one right here?
Yeah.
Yeah. So there's a bunch of old Algebra 2 stuff or whatever that y'all are just going to have to review. So I'm going to suggest if you have any questions about that was going to be my very next thing to say, by the way. So thanks for the segue. If you are maybe a little shaky about your algebra of hyperbolas, come to office hours. I'll be very happy to talk through it. No problem. The main thing that we're going to need in a class like this is that you remember which way the hyperbola goes. Does it open up this way or does it open up that way? And which way does it go based on what the equation is and how do you tell, right? So I've got a little trick for that, and I'm happy to discuss it in office hours. Just come on by anytime. Yeah. Okay. All right. Okay. Let's see the next example. The next example is going to be a little different. You'll notice I note here that a similar argument can be made for rotations around other axes, and this is a challenge for y'all to think about how would you take this argument as written here, not so much the cylindrical thing, that's kind of z-axis peculiar. But this first argument up here, how would you adapt that to get a theorem about rotational symmetry around the y-axis? And the answer is it's going to be very analogous. It's going to be a find and replace, just kind of switch the roles of the variables kinds of thing. But you got to think it through. You got to draw the corresponding picture. You got to confirm that what you get actually makes sense when you write it down. And the good news is that it's exactly what you would hope. But again, please do work that out for yourselves. And that result is what I'm going to use in this example. And you will notice this equation right here, is not rotationally symmetric around the z-axis. It's just not. Look at the x and the y. There's no fun and games that I can play with the algebra there to turn this into some expression of square root of x squared plus y squared. Not going to work. Give it a try. You're going to fail. Doesn't work. However, you can play a little fun and games and get y and z to appear only in the special form. And per the other theorems that I kind of waved my hands at a minute ago there, I claim that when y and z appear only in the special form, that means that you have a rotational symmetry around the x-axis. Again, Make sure to think through that argument. Make sure you believe it. Okay, so sweet. So again, we get to pick any plane we like that contains that axis and, go crazy. I mean, if you want to pick the XZ plane, that's fine. If you want to use the XY plane like I'm doing here, that's cool. If you're really just a glutton for punishment, you want to use some angled plane, okay, all right. I think that's weird, but anyway, I figure always pick a coordinate plane. So let's use the XY plane because I have that already drawn. The XY plane has an easy equation. You plug that in and see what we get. And not hard to see that the algebra works out like that. Again, hyperbolas, again, flashbacks, again, come to office hours if you're not exactly entirely 100%. By the way, I think this is a sizable fraction of my experience. Probably half of y'all are a little shaky on the whole hyperbola thing, right? So anyway, make sure you get straightened out. Come to office hours if you like. Persuade yourself that that is this hyperbola. And again, the big idea is that because it's rotationally symmetric around the x-axis, I can generate it by rotating around the x-axis. And again, geometric appeal, that curve rotates to make this very hard to draw, kind of weird. It's like a bowl turned on its side this way and another bowl turned on its side that way or something. But anyway, that's what you get when you rotate that hyperbola. So our original equation, however you prefer to think about it, that's what it looks like. And again, this is also called a hyperboloid. This time a hyperboloid of two sheets because, again, two chunks. How you doing? Everybody all right? All right. Excuse me. So yeah, really useful method. Again, you'll be surprised how often it comes up that whether X and Y or X and Z or Y and Z, but it surprisingly often two of the variables will appear only together as part of that special form, and then you've got a rotation argument you can make. Okay, yeah.
Are those two balls enclosed?
They're not balls. They're
shells?
You gotta, yeah, kinda. I mean, they extend infinitely. I mean, it's.
They're not enclosed.
They're not enclosed. That's right. So you have to, in the same way that hyperbolas kind of open up and they just kind of keep going, but they have asymptotes, right? They don't do like that. Right?
Is it just a hyperboloid lying down?
It is a. Did you mean to say paraboloid? It's kind. They're yeah. Well, it is a hyperboloid. That's what it is. Yeah, that's the name of it. Yeah.
Lying on the XY plane.
It's not on the XY plane. It's got an axis of rotation that is the x-axis, right? But this is a surface that kind of. You have to think about this original hyperbola. You know what hyperbolas look like.
Yeah. And
think about what you would get when you take that and just rotate around the x-axis. And it's a challenge to draw it artistically, right? But you just kind of visualize, you can see it. Yeah. Okay. All right. Okay, here's another tool for your toolbox. What I like to call deformations. This again is really important. It comes up a lot. You'd be surprised how often this comes up. So roughly speaking, I want to address this question. Suppose you have some surface, like this guy right here. Right, so we're looking at, that's a pretty easy equation that pretty much just says rho equals 13, pretty much. We know that therefore must be a sphere. Like so, something like that. So that I understand. So question, if in the equation I replace everywhere I see a z if I instead put a 2z, right, hypothetically, right, everywhere I see a z I put a 2z, and let's do that. Okay, here's a z, and I'm just going to replace it as promised with 2z. What does this algebraic move do geometrically? Right? If I tweak the algebra like so, how's that going to tweak the geometry? Right? It's a pretty natural question. One thing to be really careful about, when I say replace the z with 2z, I don't mean typographically, right? You got to look at what happens to the z and make sure that that happens to the 2z. So I emphasize this is 2z quantity squared, not 2z squared, right? So it's surprisingly easy to sort of oops that, and now you're off by a factor. All right, so what is the geometric upshot of this? Well, I'm just going to play a little arithmetic game. Let's look at this point right here and notice, I'm just going to say 3, 4, 12, and it's about where I've drawn it there. And notice that works in this original equation, and notice that it fails in the second equation. Well, of course it fails. The second equation is a different equation. Right? I mean, of course it's going to fail. And just to get all explicit about it, the 12 here was supposed to be squared to make this arithmetic work as it did initially. When I try to do it over here, that 12, the first thing that happens is it gets multiplied by 2. Now I've got a 24 that I'm squaring. The arithmetic's gone completely off track, and of course you get a different result. And in fact, here the equation just straight up doesn't work. Okay, so the problem was that z-coordinate got multiplied by 2, and therefore I wasn't squaring 12. I was squaring the wrong thing. So the big slick observation is to realize that, okay, you can anticipate that, though, and just look at 3, 4, 6. That 6, when you put it in there, gets multiplied by 2 to make the 12 that gets squared as it was kind of supposed to, in some sense. So the arithmetic of putting this orange point into the new equation is morally the same arithmetic as from putting this red point into the original equation. Everybody see that so far? Okay. So another way to say that algebraically, this process of replacing all the z's with 2z's, geometrically, all the z coordinates are just going to get cut in half, aka I'm going to smush. It's not a complete, right, flattening, right? But all the z coordinates are going to be half as big. It's going to get squished somewhat in the z direction, specifically by a factor of 2. All right, so neat effect. And by the way, this is something, mathematicians are always kind of on the lookout for, when you do something algebraically, what's the result geometrically? How does algebra manifest itself geometrically? Stuff like that. Well, I think that's awesome. So here is kind of the generalized upshot of this observation. And so think of what we just saw as an example of this general rule. Whatever you do to a variable in an equation, the opposite happens geometrically. Right, so going back up to the details, here what I did to z was I kind of multiplied that z variable by 2, and the upshot was that geometrically all the z coordinates get divided by 2. So it's just the sort of the opposite of what I did to the surface. So y'all can see this exact same sort of phenomenon in play in this next example down here. I'm going to come at this example in a slightly different way, a little bit more real world, a little bit more relatable. Suppose somebody gives me this equation and says, "Hey, what's that? What is the surface described by this equation?" And the very first thing you're going to do is think, "Oh, I see some x squareds and some y squared. Oh, I wonder if there's a rotational symmetry that I can take advantage of here." And no, you can't, because these denominators are messing it up, right? And again, if you try to play the game, if you try to fiddle with the algebra and arrange this to only have square root of x squared plus y squared, you're going to fail. because A and B are not to be assumed to be the same, and it's just not rotationally symmetric around any axis. Okay, well then what do I do, right? How can I understand this surface? And the idea is to say, look, that is a tweak of a surface that I already understand, right? This equation over here is easy. That's a sphere, no problem, perfectly obvious. I've got rotational arguments all over the place that I can use. I can interpret this with spherical coordinates. Lots of ways to persuade yourself that this is just a sphere, nice and easy. And then I can notice that all I did to turn the green equation into the blue equation is fiddled with it in just three easy little ways. Easy to notice that I just replaced my x with x over a, which is just going to stretch by a factor of a in the x direction. And easy to notice that my y gets replaced with y over b, which is going to stretch in the y direction by a factor of b, and likewise, oh gosh, I'm running out of colors. I guess I'll use red. Z gets replaced with z over c, which is going to stretch by a factor of c in the z direction. So I take a problem that I don't know how to solve. I connect it to something that I do know how to solve. Yeah, strategery, right? And then you use the fact that this algebraic tweak you can translate into geometric tweaks, and there you get your answer. And so this is what we call an ellipsoid. Hopefully no surprise, it looks a lot like an ellipse, right? So you got to know the terminology. But anyway, that's how we understand that surface. Everybody good? All right, a couple more examples, and then there's more in the book. I'm going to be real quick about these. This is a paraboloid previously discussed. It's pretty easy to look at this and see that all I'm doing is I'm kind of tweaking. For example, replacing x, replacing y, and so this paraboloid that had circular cross sections, this tweak is going to have elliptical cross sections, thus the name elliptical paraboloid. Okay, let me show you where one of the landmines is. This is an easy mistake to make, super easy. I've seen this a million times. A lot of students will look at this a squared down here and think, oh, I guess I'm stretching by a factor of a squared. That's wrong. You got to keep in mind, wherever the x is, that's where you've got to actually, whatever you're doing to the x, that's, when you replace it, that's, you've got to do all that same stuff to whatever you replace it with. So much easier to understand this instead as x over a quantity squared plus y over b quantity squared. Now it's a lot easier to see explicitly that x is being replaced with x over a, not with x over a squared. Yes?
Just going back to the previous example.
Okay, well, 2 seconds. How are we doing on this example? Is everybody okay with this? Okay, yeah, go ahead.
We divided with the ABC, and then it got stretched.
Mm-hmm.
If we multiplied,
then it would be smushed. It's not a technical term, but it's kind of squished inward. Yeah. Because it's the opposite, right? So if you replace x with ax, does that make sense?
Yeah, so it's always geometrically it's always going to be the opposite of what's happening in the equation.
Exactly. It's always the opposite. And in fact, here's an example where we did literally that, right? We replaced z with 2z. Yeah, totally. And so, so you can see it was kind of smushed in the z direction. Yeah, totally. Okay. So yeah, be real careful about this. Pay attention to parentheses. Again, this is a delicate argument. It has to apply strictly, exactly, and etc. Okay, other examples in the book. Again, this is pretty straight up. I think y'all can read that one, and other examples in the book. Okay, Moving along. So section 2.3. We're going to finally use some calculus. Derivatives will be the first thing we'll talk about. Again, there are a lot of analogies between single variable and multivariable. Very nice. But not everything's analogous, and in some ways there are things that happen in multivariable that just don't happen in single variable. New phenomena. It's not just that we're going to take single variable ideas and see the multivariable version of them. There is some really truly non-analogous, just different things that happen. So one of those big differences is, while in single variable there's really only one kind of a derivative, not so in multivariable. In multivariable there are several different, truly important, mathematically, valuable, useful things that you have to understand. Different constructions that, in their different ways, kind of make sense out of being called derivatives. So again, that's news. There is no single variable sort of version of this. So heads up, be on the lookout. You got in a multivariable calculus class, when you hear the word derivative, the first thing you should think is, wait, which kind? What are you talking about? There's several. Do you mean this? Do you mean that? Do you mean the other? Right? So be careful. I do like to point out that there is something a little bit unnatural about using the same word to describe different things, right? Awkward, right? And we're not going to use exactly the same word, but we are going to borrow. We're going to. All of the names will involve this common word, and that's because all of these concepts have a common characteristic. And again, I think this is a big deal. The unifying feature of all derivatives in multivariable calculus is that in their different ways they relate input changes to output changes. And you can think back to single variable calculus and various different interpretations of the derivative, right? In single variable calculus, it's a slope, it's a rate, it's a factor, it's a various different interpretations, all of which, in their own ways, relate input changes to output changes. So be on the lookout as we talk about different kinds of derivatives for that. I'm going to start with partial derivatives for a combination of appealing reasons. It's nice that they're easy. It's nice that they're relatable. You're going to see the relatability in just a couple of minutes, depending on how time moves here. We're following the pattern that this book does. Here's the problem. I think it's important to note that even though we're going to start with partial derivatives, this is really not the best way to think about multivariable derivatives. They're not my favorite kind of derivative. They're not real. They're computationally convenient. This is nice and all, but like when you're thinking 15 years from now, right? When y'all are thinking, but you're mid-career, right? And you're thinking back to the old days of college and that multivariable calculus class I had to take. So what's the deal with multivariable derivatives? Not this. Please don't let this be what you're thinking of. This is not the best way to think about multivariable derivatives. We're going to see probably on Friday what I consider to be truly the best way to think about multivariable derivatives. Again, time depending. So anyway, this is just a foot in the door. I want y'all to think of partial derivatives as being a first attempt that is going to end up not being a complete failure. I think that's a pretty good way to think about it. All right. And here's how you do it. It's a pretty simple little process. If you have a function with several variables, play make-believe. Pretend that most of those variables aren't variables. It's almost like a wishful thinking sort of a thing. You're looking at a function that has several variables, and you're like, wouldn't it be nice if only one of those was actually a variable? I'm going to pretend that only one of those is actually a variable. Right? It's kind of cheating a little bit. But anyway, if you insist that they all stay constant except for one, if you think about it, this initially multivariable function now, what used to be a bunch of variables is now a bunch of constants, except for one of them. So in fact, we really kind of just have the one variable. arguably what you have is a single variable function. And you then say, okay, I'm going to take the regular, good old, plain old regular derivative of that single variable function. So this is called the partial derivative notation. Do be careful to notice that this symbol is not a D. It's very important that it's not a D. If you write this as a D, you're taking literally a single variable derivative of a function that is not a single variable function. It's wrong. You just can't do it. It's not okay. So, annoying though it is, you have to be careful about making this thing that looks a lot like a D, make it conspicuously not a D. And by the way, it's also not a lowercase Greek letter delta. So it's annoying. I literally think they just made up a brand new symbol when they did this. So that's the most common notation. And it looks like we're out of time. I'll say a couple more words about this next time before we pick back up. Okay, see y'all later. Have a good one. Oh, and if you came in after I did attendance, make sure that you come talk to me, and you got to explicitly make sure that I mark you as present. Give me just 1 second to get the recording stopping.